Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our lecture topic today is Applied Electricity for Beginners. This course covers General Engineering and Technology, known as GET 201, which is a curriculum for all engineering students under CC Mass. In this lecture, we'll be looking at electrostatics, electromagnetism, and magnetic circuits. Please follow me in this lecture series by subscribing to my YouTube channel at https://youtube.com/@ndinechimichaelc. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. You can also listen to other interesting engineering lectures by subscribing to my YouTube channel, which is, as stated, https://youtube.com/@ndinechimichaelc. So we start with the fundamental concept. We say a body or an individual atom of that body is said to have an electric charge when it acquires excess or is in deficient of electrons. When there are surplus electrons, the body is said to be negatively charged. On the other hand, if there is a deficiency, the body is said to be positively charged because electrons carry negative charges. The starting point in the study of electrostatics is usually from the experimental investigations by Coulomb, who likened the electrostatic field associated with the charge on a body to the gravitational field associated with the mass of the body. So, Coulomb, in his law, states that the force of attraction or repulsion between two charged bodies is proportional to the magnitude of their charges and inversely proportional to the square of the distance between them. We can see that in Fig 1, that you have two charges, Q1, Q2, and there's distance between them. That is what Coulomb is trying to define, that this force of attraction or repulsion is proportional to the magnitude of their charges and inversely proportional to the square of the distance between them. That is represented in equation 1, that F is equal to Q1 Q2 over R squared, where K is a constant, which we will see very soon. So if R is the distance between the two bodies, and Q1 is the charge on the first body in coulombs, and Q2 is the charge on the second body in coulombs, and K is a constant which is equal to 1 over 4 pi epsilon, giving us 10 raised to power minus 9 over 36 pi in farads per meter for free space. So if we substitute the value of K in equation 1, it will give us equation 2, which is F equal to Q1 Q2 all over 4 pi r square epsilon naught, where epsilon 0 is called the permittivity of the medium between the two bodies. This force acts in the direction of the line joining the two bodies. If Q2 is assumed to be the test charge, and if this charge is placed in an electric field where the field strength is E, then the mechanical force acting on the test charge is given as F equals Q times E in newtons per coulomb or volts per meter. Therefore, we can define the electric field strength E as force per unit charge, which gives us E equals F over Q, which is equal to Q1 over 4 pi r squared epsilon naught. We call that equation 3, but we note that Q is equal to Q2, which is the test charge, as we specified above. Now, we come to another term, which we call the electric flux, phi, and electric flux density, D. The electric flux density, D, which was called displacement by Maxwell. Of course, in future, we will meet all the Maxwell's equations, which will give us more insight into this flux density D and current density J. But for now, we limit ourselves to flux density D. So we say the electric flux density D, which was called displacement by Maxwell, is defined as the electric flux per unit normal area. If the spherical surface of radius R, as shown in Fig 2a, where R lies between R1 and R2 is considered, then the total flux equals Q and the area is equal to 4 pi r squared. So if you look at that Fig 2a, you are seeing a concentric cylinder in which the inner one has radius R1, the outer one has radius R2, but we are considering an arbitrary R between R1 and R2. As we go on, you see that this helps in analyzing coaxial cables or conductors that have, outer surface and inner cylinders. So if we look at that Fig 2a, you see that D, which we call the flux density, is equal to total flux over the area, which is Q over 4 pi r squared. If we match it with other equations we have met, you see that D is equal to epsilon naught E. We say where the surface is not everywhere normal to the electric displacement, then the total flux is given by phi equals integral of D ds to be equal to Q. Because it is not normal, so it is not uniformly distributed, then we have to do the integration over the surface S, and that will give us the total charge in that surface. So we call that equation 5. Thus, The integral of flux density over a closed equipotential surface must be equal to the enclosed charge in that surface. That brings us to another level, which we call the Gauss theorem. This states that the total electric flux passing through a closed surface is numerically equal to the electric charge enclosed by the surface. It gives us that the phi is equal to the integral of the phi over the surface S, which is equal to integral d ds equal to the integral of ds is still equal to q. So we have seen how Coulomb got his own charge and how Gauss is also trying to arrive at the same point. Now, so therefore, for a charged particle and a sphere of radius r meters, the flux density will be equal to q over 4 pi r squared coulombs per meter squared. If you say that, it means that d times a is equal to q, where a is the area of the surface giving us 4 pi r squared. So if we do some adjustments just to get all we have been saying into the terms we know, which is E, D, and epsilon, then we can have that equation. But it is important to note that for free space, epsilon is equal to or represented as epsilon naught. Otherwise, epsilon is given as epsilon naught, epsilon r, where epsilon r is the permittivity of the medium. Remember, we have said that epsilon naught is the permittivity of free space. At this point, we note that the coulomb is the unit of electrical quantity, and it is defined as the quantity of electricity passing a given point in a circuit when a current of 1 ampere is maintained for 1 second. As we go on, we also define other terms like the ampere. Electrical potential. So if we consider the work done in moving a point charge, like we have seen in figure 1, moving a point charge plus Q in an electric field of strength Q E dx. Hence, the electric potential defined as the work done thus electric potential is defined as the work done by the extraneous force against the forces of the electric field in moving a particle bearing a unit charge from one point to another. Sorry, I'm having issues sharing my issues sharing my issue sharing my. Okay, we continue. The difference in potential between x1 and x2 is given as dv equals minus e cos theta dx. At this point, it seems I'm having network challenge. Okay, let's continue. Please, can somebody chat and confirm that you are still seeing my slides? Okay, we go on. Yeah, we say that electrical potential or electric potential is defined as the work done by a strenuous force against the forces of electric field in moving a particular a particle bearing a unit charge from one point to another. So, say a particle moving from x1 to x2, which covers a distance dx. Any potential that can move a charge from x1 to x2 is defined as electric potential. So the difference in potential between x1 and x2 is giving us dV equals minus E cos theta dx. Of course, if you differentiate it, dV dx will be equal to minus cos E cos theta. If theta tends to 0, or it means that dx is also tending to 0, so it becomes that dv dx will be equal to minus E. Therefore, v will be equal to minus integral Ex dx. We call that equation 7. Okay? Where V is the potential at point X, or the work that must be carried out in bringing a unit charge from infinity at 0 point or 0 potential to this point. The negative sign is an indication that the work is against the forces of electric field. Therefore, the potential difference, PD, is the difference of potential between 2 points of a conducting wire carrying a current of 1 ampere when the power dissipated between these points is equal to 1 watt. It is now possible to evaluate not only the electric field distribution of most conductor systems, but also the potential difference and hence the capacitance. So, capacitance of a body, we can say that it's possible for this body to acquire or lose charges. If it does, its potential changes by an amount which depends upon the charge gained or lost and the electrical capacitance of the body. When a voltage is applied between a neighboring pair of conductors, an electric field is set up between them, while an equal and opposite charges appear on their surfaces. If the conductors are in close proximity and of sizable area, the total charge on each may be considerable. Then the pair of conductors exhibits significant effects when placed in electric circuit if there is variation of voltage. In fact, an alternating current passes almost as if there is direct connection between the conductors. Such an arrangement constitutes what is known as a capacitor. Capacitance, therefore, is defined as the ratio of the charge on a conductor to the potential when all neighboring conductors are at 0 potential. So capacitance C is equal to Q over V, and the unit is in farads. Consequently, we can say that current I passing through the capacitor as a result of the capacitance is giving us I equals C dV over dt. Now, these capacitors, when they are connected in parallel, they behave differently from when they are connected in series. So we have to consider these capacitors when they are connected in parallel and when they are connected in series. Let's start with the connection in parallel. So consider two parallel plates with area A separated by distance D, and with the field normal to the parallel plates. If Q is the magnitude of the total charge on either plate, applying Gauss' law to the closed surface gives D times A equals Q. But we know that Q is equal to epsilon E over D. If we substitute that, we also see that Q is equal to epsilon V. If E is clearly uniform and of magnitude V over D, with V being the voltage between the plates, then it means that Q is equal to E epsilon VA over D. Therefore, C is equal to Q over V equals epsilon A over D. Of course, where D is the distance from fig 2, D is the distance between the two plates. We call that equation 9. Of course, we know that epsilon, if it is not in free space, is equal to epsilon naught epsilon r. So if we substitute that in equation 9, it gives us equation 10. Now, this farad we are talking about is the capacitance of a capacitor between the plates of which there appears a difference of potential of 1 volt when it is charged by 1 coulomb of electricity. So if you look at that fig 2, it gives you what picture of what we are saying. Two parallel plates, one having positive charge, the other one negative charge. Distance separating them is D, and of course, we have a surface area between them. So the two metal plates separated by an insulator constitute a capacitor. In some cases, the capacitor is called a condenser. Such an arrangement has the capacity of storing electricity as an excess of electrons on one plate and deficiency on the other plate. Now, these capacitors start to behave differently depending on how you keep them. The important thing is bringing them to real life examples. For instance, if you have seen a coaxial cable, the cable you normally use to connect your TV from the external antenna. If you cut it, you see the cross-section area that there are two conductors there, one at the inner point and the other at the outer surface. It means that the current flows in one and returns through the other one, and therefore sets up a capacitance around them. If you don't handle it very well, it becomes a problem. And we call that concentric cylinders because there are, it's a round thing. just as shown. You have radius A, you have radius B, and between A and B, you have radius R, and you can integrate over that surface from A to B and see what is happening. And we are saying that when you do that for a concentric cylinder, the electric charge E, which we call the electric potential, will be given as Q over 2 pi epsilon naught R L. If you look at that fig 3, you see L, which is the length of the cylinder, while R is the radius of the points between A and B that you are considering. So say if you do that and do your small mathematics, you will arrive at equation 14, which says that C is equal to Q over V equal to 2 pi L epsilon natural log of B over A, ln B over A. Also, you can do that for parallel cylinders. If you look at your transmission lines, when you have two wires overhead, also the two wires set up capacitance. So you must be able to do some, computations to know when the effect will be detrimental to transmitting your signals. The parallel cylinder can, best be represented when you have your parallel wire pairs used in, when you are connecting two gadgets. So, just like before, if you do that analysis, you will see that what you will have is that one of the cable will be, creating its electric potential, the other one will be creating. So the total potential in the transmission will be E equals E1 plus E2, which we call equation 15. So if you do your little mathematics, you get to equation 16. We hope that you will follow in that and arrive at equation 16. They are straightforward mathematics. So we also have types of capacitors. We have a capacitor. So this consists of one set of fixed plates and another set of movable plates. It is used in radio sets just to vary capacitance and help you to select different channels. When we talk of channels here, we talk of the frequencies you are looking for. Then you have paper capacitors, we have the mica capacitors, which is used in high frequency circuits. We have the ceramic capacitors, which is used when high temperatures are required. We have polycarbonate capacitors. We have electrolytic capacitors. Probably as you go on, you'll be meeting more of these electrolytic capacitors. So the electrolytic capacitor is commonly used for some reasons. One, the insulator resistance is comparatively low. Two, it is stable for circuits where the voltage applied to the capacitor never reverses its direction. Three, it's used also where large capacitance is required, such as in your rectifier circuits. So these capacitors, as we said, can be connected in parallel or in series. When capacitors are connected in series, you can easily do your computation using equation 19 to find the equivalent voltage associated with that. And that is easily done by saying 1 over C total, that is, C total here is the total capacitance of the circuit, will be equal to 1 over C1 plus 1 over C2 plus 1 over C3 until you get to Cn. We call that equation 20. So it is basically as simple as that. So you can also find equivalent of capacitors in parallel. When you have capacitors in parallel, you see that you just add them up. You note here that it is the reverse of what you have when you are considering resistances. The assumption here is that you have met this in your 100 level physics, so we are not going to waste so much time in that. Then we talk of electromagnetism. So whenever flux linkage in a circuit is changed, there is an induced electromotive force known as EMF. Lenz's law tells us that the direction of this induced EMF is such as to tend to oppose the change in flux, that is, the change in current. So when we talk of this electromagnetism, two things come in mind: self-inductance, and we say when an EMF is induced in a circuit, the self-inductance is proportional to the rate of change of flux linkage within the circuit. So if we consider an A-core coil carrying a variable current as shown in Fig. 7, the flux will be proportional to the current. If you look at Fig. 7 and you connect the coil carrying current on both arms, you see that the EMF that will be induced if you connect one end, the EMF that will be induced on the other will be equal to L di dt, where L is the self-inductance of the material you are using. So the unit of self-inductance is the Henry. In a coil of N turns, the induced EMF is given by N d phi over dt, where the N d phi is the flux linkage of the circuit. So if we combine equation 21 and 22, it will give us L di dt equals N d phi dt. If you substitute for L, it will give you that L is equal to N d phi over the I. And we note at this point that a circuit has a self-inductance of 1 Henry when an EMF of 1 volt is induced by a rate of current change equal to 1 ampere per second. Take note, say current change. In other words, we are talking of alternating current that will be changing in phase and in amplitude. Also, we can have what is known as mutual inductance. So if we consider a varying current I In coil 1 of fig 8, the changing current I1 establishes a magnetic flux phi 1. Part of this flux links only coil 1 and is called linkage flux, denoted as phi 11, please not phi 11, but phi 11, showing that it is the flux that is only linking coil 1. The remaining flux, which we call phi 12, links also coil 2 as shown. If you look at the dotted line, you see that some of the flux only stopped at the left-hand coil, while some crossed over to link with the right-hand coil. So we call the one that stopped only on the left-hand side phi 11, while the one that was able to cross to the second coil we called phi 12. So with that, we can see and develop an equation for the EMF developed in coil 2 as a result of the one or the current coming from coil 1. And it is given as equation 23, which is E2 equals N2 d phi 12 dt. Now, the N there automatically shows us that the number of turns is of importance. And because that current